Yeah, but it's time. I think it is. Good morning. There's still plenty of room further up front if people feel cold and want to huddle together, but it's a big room here. There's even some seats up at the tables here, so we should get going. I think the blue sheets are already out, might have started circulating, so please sign those. You are here for the reliable and available wireless BOF. If you don't know the distinction between a BOF and a working group, please go look it up. But we're trying to figure out if there's some interesting new work for the IETF to do here. So we're not going to talk necessarily about exactly how problems will be solved, but go check on that. I'm Eric Nordmark, and I'll let Rick introduce himself.
Good morning, everyone. I'm Rick Taylor. I will apologize in advance. I have a cough, so if there's sort of consumption-style coughing coming from the chairs, please ignore. Just to follow up with what Eric said, this is a working group forming BOF. So there has already been a raw BOF to discuss topics around this area, and it was successful and well represented. So this is now an opportunity for us as IETF attendees to decide whether we wish to form a working group to work on this, but we'll get into that in more detail.
Oops.
If you just go left and right, it does 4 pages.
So this is the note well that applies to this meeting as well as all of the other IETF meetings. If this is new to you, please go read more about it. Keep in mind that we're taking minutes. The meeting is actually being recorded. We keep track of presence. We will have some remote presentations as well using MeetEcho, and I think we have people that are listening in over MeetEcho as well. So a number of people there already. So first of all, we need a minute taker. Do I have a volunteer? Thank you, Ethan. Could we have a second volunteer as well to keep track, just in case the discussion gets heated? I don't think it's...
We'll be using Etherpad, which is a really good tool and is easy to use, so you're not committing to a whole session of typing.
Yeah, people can always keep an eye on Etherpad, and if things look a bit... if there are things that they would like to correct, there's ways of doing that as well. So, somebody volunteered already to be a Jabber scribe. Yes, thank you. So we have that taken care of. There's a mailing list. The materials are all uploaded. I've done some updates as of this morning. And we have a couple of presentations. So this is the agenda for today. We want to touch a bit about use cases. There's a use case document that talks about lots more, but we want to at least go in and show there's something that's a bit different than people might have thought about before in this space. And problem statement, the purpose here is to get people to understand what the working group a potential working group is proposing to do, and the scope of that work. So any sort of agenda bashing at this point in time? So as I hinted at, the purpose of the BOF is to understand the problem statement as well as the scope of the proposed work, and not start discussing necessarily the solutions. Often it's useful for the people assembled here to understand that, oh, it's possible to solve this. We're not trying to solve some unsolvable problem. But then the other part is sort of gauging the interest of the people that are here, as well as on the mailing list, to do work in this space. There's likely to be some things that tie in more with radio and channel aspects here. So if there's people that are sort of experts and working in that field, this might be interesting in terms of sort of characterizing things. And this actually applies even in fixed wireless deployment. So that's one of the things that are interesting in this space. So there might be a sort of a slightly different community of people that we can encourage to come and join us to help with this work that might not traditionally come to the IETF. And the intent is, you know, to leverage existing work, of course, right, from other working groups as well as other SDOs. So that's it for the introduction. So Carlos, yeah. So now you can figure out where you put the tabs.
Okay, can you hear me? So I'm Carlos Bernardos. I'm from UC3M, and I'm gonna present this system draft. Okay. So I think it's better now. So I'm gonna present this system document on use cases that is covered on the guides that you see on the slide. So, oops, the typical problem with this. Yeah, but I think it's like scrolling more than.
Just say it like.
Okay, so in the draft there are 6 use cases documented. For the sake of time, I'll try to be very brief, just for allowing for discussion on the actual both. So there are 6 use cases. I'm gonna just talk about one of them, the wireless for industrial application. In the draft, for each of the use cases, basically we describe the use case, the generic scenario. We justify a bit the need for wireless, which is pretty obvious in most of the cases. Then we go a bit into the specifics of each of the use cases, and then based on that, we identify some of the actual requirements for reliable and available wireless from each of the use cases. So next one, please. So for the wireless and for industrial application scenario, this is a picture. I will not go into the details, of course, that tries to exemplify what this use case is about. So it's about having a factory kind of a scenario in which we have machinery that we need to control, and this control is remotely, so we need a remote connection between this control and the actual machinery that is most likely wireless because of the different characteristics. And in addition to this control traffic, we may also have other type of traffic for generic monitoring and diagnosis for the operation of the traffic. And in this kind of environments, we may have multiple types of wireless technologies operating at the same time. So we may have simultaneous links and heterogeneous kind of technologies working in parallel. So we need to operate those in a way that ensures that each of the types of traffic gets the reliability and the actual conditions that they require to operate properly. Next, okay, now it works. Now it works. Thank you. So going a bit more into the specifics of this generic scenario. So what are the specifics? We need to support, or we have heterogeneous technologies, most likely wireless. It may be that in some of the segments of the connectivity we have also wired, but we have mostly wireless technologies. We have that we need to have support for multiple links, or use of simultaneously multiple heterogeneous wireless links, in order, because of the specifics of each of the machinery, or because we need to ensure a high reliability. We have that these conditions, or the conditions of the links that we have, may be variable in time, even though we may have fixed scenarios with low mobility or no mobility at all. But because of the intrinsic radio characteristics, those links may suffer from variation that we need to cope with. And as I mentioned before, we may have different types of traffic at the same time. So for example, the control loop kind of traffic that, of course, reliability is key in this kind of a scenario, plus the not so demanding in terms of reliability, monitoring and diagnostic traffic. Those are two examples that we may have in this scenario. So based on that, what are the specific requirements for RAW, the main requirements for RAW in this, or for this use case? Well, there are particularly two, although there are a few others, that are first, the solutions need to be backward compatible in the sense that we need to support both this traditional, less demanding traffic like monitoring and diagnostic, plus the new traffic or the traffic that really demands reliable and predictable wireless behavior, like the control loop traffic that I mentioned before. We also need to support heterogeneous wireless technologies operating at the same time, as I mentioned before. So those are the kind of key two new requirements that demand solutions in the RAW space. And I don't want to spend much more time, so just as a quick summary, so we have different use cases that require wireless connectivity with reliable and available behavior. We have identified already 6 in the draft. We are working already in a couple more, for example, the digital aeronautical communications and smart grid. And in terms of next steps, in case this working group is formed, we would like, of course, to continue identifying potential use cases for RAW, and also to continue working on existing ones in terms of characterizing the actual requirements that we need for the potential RAW technologies to be developed. And that's basically all in terms of very short summary of use cases. So if you have any question, comment?
Hi, this is Umar from FutureWay. Just from the deployment scenario, the first slide picture you've shown, it shows all layer 1 and layer 2. Is it the scope or any layer 3 stuff happens, intended to happen here?
Well, the scope is to actually, I mean, that will be a bit solution space a bit, but the scope is to support multiple technologies and how to properly configure and use those multiple technologies in order to support or to provide the reliability and mainly reliability characteristics for the whole operation of the traffic. I don't know if that answers your question. I don't know exactly what you...
Maybe I can try, but...
Yeah.
So the working group is proposing what to do in these, I guess, black boxes, right? The thing that actually provides the layer 3 service using multiple layer 2 technologies.
Multiple layer 2, okay.
Yeah.
So because all these 6-ish and all these are layer 1 maybe, and in the middle, yeah.
But it's the boxes that interconnect that, so you can provide a service across this whole network that is reliable and available using different underlying technologies. So that's the key thing it's illustrating, right? But it is about layer 3. Just like DetNet is about layer 3 using different layer 2 technologies underneath.
Okay, thank you.
Okay. Pascal?
So clearly one of the main discussions we need to have today is to establish a scope for the work that we intend to do, and basically what kind of problem we want to solve. And so we started a draft, and we've been working quite a lot on that draft since the last IETF, where we had this informal meeting. And basically, here's the content of the draft for a minute. So you will see that the draft is not only about the exact prime, that will be one of the last sections, section 7, but it also deals with positioning the work inside the IETF and figuring out what's in and what's out. In particular, the raw problem starts where the current understanding of routing and centralized routing stops. So basically, we expect that the centralized routing, mostly in DetNet, from which we inherit, will build a routing with enough reliability, availability for wired applications and pretty much the pre-off functions that .NET defined. And the routing will be programming the forwarding once and for all. And the forwarding will be a simple application of what the routing has decided. And that's probably enough for wires, but for wireless, we see the need of decoupling those two a little bit more and providing some local intelligence for it. And that's pretty much what the draft tries to discuss. So we'll go into more detail about that. Okay, so the first thing that the draft does is terminology, because when we start those discussions, people wonder, hey, are we talking about the same thing? So it's really important to define the terms we'll be dealing with. The first term, reliability, and actually availability is like that as well, both come from automation world. So it's nothing really specific to IETF or internet. Those are terms that you find for everything automation. The first term, critical term, is reliability, is how well a certain system will be able to perform the expected function. And in our case, the expected function can be to deliver the packet. If you talk about determinism, then it will be to deliver the packet timely. And how reliable the network is how well the network can deliver those packets in due time. So you'll have to establish metrics to measure the reliability. A usual metrics in the industrial world is the mean time between fault, or mean time between errors. And you will find as you work on Rho that we might be interested in other metrics, and another critical metrics is the number of consecutive faults. If you have a control loop, which is one of the usual applications of automation networks, you can actually it's totally acceptable to lose a packet. Packets get lost. But if you lose 4 packets in a row, the system will go into emergency stop. And that's one thing that is not acceptable. So the number of consecutive errors becomes a key metric for your reliability. Okay, so the first phase, one of the phase and one of the interesting things in this document is to actually define reliability, and with it, define the metrics by which we'll be able to assess the reliability that our networks will have to ensure. Second thing is availability. So it looks kind of simpler in our case. So the availability is basically the amount of time the service is up divided by the total amount of time. And so like if you have a safety network, you want 100% availability because some lives may be at stake. That really boils down to putting together redundant systems. If you talk about safety, that's when you start having different systems ensuring the same service, possibly different systems with different implementations and possibly different protocols. And you realize that the safety people are really, really concerned with diversity. Diverse systems, diverse networks, maybe wireless technology combined with wired technology, maybe some protocols combined with other protocols, and possibly different implementations. So diversity spans all aspects of a certain system, including the network. And we'll find that wireless also includes its own collection of possible diversity. And part of the raw game that is not present at all in the wired space is how to exploit the new diversity that the wireless enables. And finally, there is this third term which will be kind of critical to us. We coined Pareo. It can still be changed, but it's kind of the wireless version of what we inherit from .NET, which is pre-off. So pre-off in .NET means packet replication, elimination, ordering function. It really means, okay, I want an available path. I want to reach 10 nines. So Ethernet will give me 5 nines if I have 2 parallel paths with Ethernet, and they are completely independent, completely non-congruent, and blah, blah. Then statistically, if I have 5 nines on the left, 5 nines on the right, I get 10 nines. Okay? And that's the replication typically at the ingress and the elimination at the egress, so that you get a single packet out. And guess what? As you do this, you might actually put the packets out of order. So that's why they have this ordering function typically at the egress. And that model is also typically quite enough for wire, meaning that usually you'll get 2 parallel paths, you'll be monitoring their activity and ensuring they're still up, and that will give you a viability and 10 nines. So the routing will actually build 2 TE paths, set that up, install a flow over that, and you'll be all set for deterministic networking. For wireless, it's going to be a little bit more complex because the medium itself is not deterministic. So you cannot even claim, oh, I'm building a deterministic network. And you will see that, hopefully, in our specs. If ever you find the term deterministic, it's going to be quote unquote, right? We try to avoid using the term deterministic. And that's why, even though we inherit from .NET, we are not claiming we're going to bring you a deterministic network. We are going to bring you a network which is as reliable and available as possible. And actually, the routing we'll have to sort out, to build a path and a collection of paths which, over time, ensures the quality that you want. The prime is, as you do this, the path or the collection of paths that the routing will have to devise for the wireless will probably be oversized for a particular moment of time, meaning that if you really want so many nines, that means you have probably like 3, 4, 5 different paths that you could use in parallel. Some of them single hops, some of them multiple hops, etc. Some of them over possibly different technologies. If you go and use everything all the time, so if you really flood this graph that the routing has provided to you all the time, that means overuse of energy and overuse of constrained spectrum. In many applications, we cannot waste those resources. On wires, again, it would not be a prime. You just push the packets on both paths and you're all set. But on wireless, energy and spectrum are critically important. And guess what? Since the links are not so viable, you really need to have a lot of redundant diversity as you build those paths. So now you see the tension, right? On the one hand, the routing has to give me a very diverse path of very diverse possibilities to get from A to B. But on the other hand, if I use all this diversity all the time, I'm wasting my spectrum and my energy. And so this thin pipe that exists between the PCE and the forwarding, which was just simple programming for the wire, now has to become a lot more intelligent so as to wisely use the resources that the routing has told you, hey, you could use this hop or this hop or this hop to get from A to B. Yes, I could, but at this time, for this packet, should I really use everything or should I use a subset of it? How can I decide? So that's going to be the prime that Ro will be discussing. So we're talking about possibly a large network. So I'm not sure I can actually... Well, so we have a potentially large network, but and the centralized routing, what we usually call a path computation element at the IETF or PCE, sees this whole network and will decide for a number of traffic engineered paths, which particular hops can be used to go from A to B. So we have, for instance, a small graph which is here somewhere. And it's a control loop between maybe a sensor here and a programmable logic controller. So it's the first half of a control loop between a sensor and the programmable logic controller. And we want that all packets from the sensors reach the PLC within due time, and you never lose 4 packets in a row, something like that. So on the one hand, you realize that the view that the PC has of the network is a very large network. That view cannot be instantaneous because just talking to the controller takes a lot of time. Also, it's a very large view, and solving the problem of many paths like this one, which may use the same constrained resources, is an NP-complete problem. So solving this problem at the scale of this large network with many paths like this is a huge computation, and it does not happen quickly. It happens actually rarely, meaning that when finally the computer decides, oh, here is how I'm going to lay out all those paths, you expect that the paths that have been built are usable for a large amount of time. So the computation is slow, the talking with the controller is slow, and what the controller builds is expected to be there for a large amount of time. Which also tells us that the redundancy that has to be put in place has to be capable to handle the short-term breakage that happen all the time on radios. Because if you look now, if you narrow down to this particular little graph that the routing has selected between node A and node B for this sensor to PLC, you realize that there are a number of wireless hubs. And those wireless hubs, they tend to work most of the time, like 80% of an hour. But at a very particular time, there might be some metallic object passing through between the sender and the receiver. And guess what? For half a second, the link will be down. Can you go back to the routing and say, hey, I need to recompute my routes? You can't. That's not the same time scale. Okay, so now we realize that we have a time scale and some particular metrics, which are what we tell this PCE and on which the PCE will build those paths for a long time scale, for a long time. But at the same time, those wireless hubs will go available, unavailable, available, flapping, quote unquote, for much smaller amounts of time. And we need a much faster reaction and much more narrow and fine-grained understanding of this particular small network within the network. But we need this information all the time. And the type of metric that you will use now is no more a statistical 80% availability over hours, but more like, hey, does it work just now? So more like on-off Boolean. Or something like, what is the current speed of my file? Because many of those files, it's true for .11, it's true for 15.4 now. You can tune the file rate to adapt to the propagation. And guess what? That changes, which means that the amount of traffic that you can send on a particular segment changes over time. And as you decide where to place your reliable, available flow, you have to account for the current speed of those links. Okay, so you see that on the one hand, you've got metrics that are really available, average speed or average availability, blah, blah, that can be pushed to this PCE to solve the global problem, which is a very hard problem with many paths over a large network. And on the other hand, you need another set of metrics which are a lot more instantaneous and that really tell the forwarding for this particular small network how to use wisely all this overload of resources that the routing has said you could be using. So basically, now we've kind of introduced this new concept of a path selection engine, which is this overgrown pipe between the PCE and the forwarding that is being programmed, where actually you may take decision of tuning the forwarding at a very fast pace based on information that is made available within this very small topology that we just saw. So the core of the raw program will be to work on this new element that we call a path selection engine. And a side effect of that is, since we are talking about wireless, the work that the PSC will have to do will have to account for the richer capabilities that radios have. In particular, in the pareo functions, we introduced the capability to do retries, and maybe the retries fail, and if they fail twice, then you try another hop, a different next hop. So that's part of what we call ARQ, retries, the capability at layer 3 to decide, hey, I can try twice on the left, but then I might go right. Or I can trigger replication because it didn't work well on the left, so maybe I feel better if I try both next stops at the same time. And you can see on this table, the PSC is really a different kind of beast. The PSC does not do route computation. The routes are there. The PCE has defined the routes. The PSC is in charge of using them wisely. The operation for the PSC happens within this small network, this small overlay that the routing has decided should be used for this particular reliable available flow. The decision of how it's going to be used could be source routed. The ingress could flag the packet and say, oh, on the first stop it's going to be replicated, but then there will be no more replication. Or maybe there will be cross copy between one path and another path. I guess the room is in the dark now. What did I say? So we are talking about different time scales. We are talking about different metrics. We are talking about different pace, right? So that's really the key difference between this PSC, which really lives somewhere on the southbound interface, and the traditional PC programs by forwarding that we have in .NET. So is it even? Okay, so the other question is, okay, you know your wireless hop is not deterministic. Can you even achieve what you claim you're going to achieve? Well, we claim, and we'll see more when we discuss the technologies, that there are more and more wireless technologies that provide more and more guarantees, and the way those guarantees are improved widely is through the use of time division multiplex and scheduling. As you schedule radios, you will get the usual benefits that you expect on wires. So for those of you who participate to TSN or .NET, you realize that scheduling traffic, in particular scheduling all the critical traffic, allows us to put a lot more high-cost traffic on a given link. Usually, you're used to put like 10–15% of highest cost traffic on a link. After that, you start getting statistical effects. If you schedule your traffic and you know exactly how much is going from everywhere, like you do in a plane or you do in a TSN network, now you can load the network a lot more. So that's one of the good benefits that you can find from scheduling. One critical benefit that we have in TSN from scheduling is that we ensure that we never get too many packets in the outgoing queues, because pretty much all the loss that you can find on an Ethernet network is collision loss. Collision loss being I have 10 packets on my outgoing queue, but there are 5 places. Right? So I have to discard packets because there's just not enough room in my queues. On wireless, most of the loss will be in the air. So we'll see that scheduling also allows us to reduce the collisions, not in the outgoing queue of the Ethernet, but really in the air. And finally, the key advantage that TSN derives from scheduling is if you know exactly where the packet is within each period of time, then you know how many periods of time it takes for the packet to go from A to B. So at the end of the day, TSN and .NET over it will give you guaranteed latency. So those are the usual benefits that you can derive from scheduling. In wireless, we derive even more benefits, and that's kind of cool. The first thing is, if you know, and for instance, we mentioned 60 earlier, if you know when you transmit something, if every transmission is scheduled, now you can live without interference space. You can live without backoff, which is really empty space in your transmissions. And that's kind of cool if you're battery operated, because you don't want to be listening for the void. The second thing is, again, if you're battery operated and you have, I would say, relatively rare transmissions, you don't want to be listening in case of somebody wants to talk to you asynchronously. So you want to know in advance when A is going to talk to B, and A is going to wake up at that exact time, and B is going to wake up at that exact time. And 90% of the time, they will be sleeping. And that's how you extend the battery life. Actually, those battery-operated devices, they sleep more than cats. So being able to avoid empty space in the air, being able to sleep most of the time, are additional advantages that are derived by from scheduling the network. Now, if you're used, again, to the way TSN operates, you'll find that the way we provide the raw properties on wireless are different from what you do on wires. First thing is, like I said, on wire, the only place I can have a collision is my own outgoing queue. So the core of what TSN will be doing there is, first you schedule to make sure you don't have too many packets, and then if you have a non-deterministic packet being sent on this transmit queue, but you've got this urgent deterministic packet that you want to send in the middle, then you can snip-snap the current packet, put the half that you didn't send on the side, send your deterministic packet, and resume the transmission of the lower priority packet. And that's that's easy because you own the whole thing. You own the silicon that's transmitting, and the medium is the unidirectional transmission of your Ethernet towards the switch. In the air, it's different. This is a shared medium. There can be tons of things which are happening on that spectrum. And the only way to kind of avoid all forms of collisions is, again, diversity. If you're facing a white noise, maybe sending a spike of energy on a very narrow band channel is the way to defeat that noise. On the other hand, if you've got a very small spectrum with a lot of energy in it, then using the spread spectrum technology is the way to go around it. And now you realize, hey, if I use a single radio technology, I have less probability of success than if I'm capable of using two different technologies which have different properties on the way they use the spectrum. So again, diversity, diversity, diversity. Diversity is the key to give us reliable and available transmission. And pareo is actually the term we coined to express all those forms of diversity that we want to use. So a key one that does not exist in .NET is ARQ or hybrid ARQ. So that's the retry. ARQ is the retry. Hybrid means you can do some forward error correction with it, meaning that, for instance, if I have like 2-3 paths, and I do some network coding with my packets, I send A, B, C, D, 4 segments, I can send a 5th segment, which is the XOR of the first 4. And if I do that, and one of the 4 is lost, then I can use the 5th one to recompose at the end what I lost. The amount of network coding that you apply could depend on your appreciation of the reliability of the network at this particular moment of time. So you see there's a lot of intelligence that could take place in order to ensure like the number of 9s that I want, or the number of packets lost in a row that I want to maximize, to ensure that at this precise time. And that could be dynamically tuning the capabilities that are there. So we are not installing the routing, but we are using all the capabilities that are there very wisely to optimize the balance between, in the one hand, energy and spectrum, and the other hand, reliability and availability. It's this balance that we want to play with. So we kind of looked at how we interact with different working groups. Clearly, we inherit us from the MANE architecture. We'll have the central computation because you need this God's view of the network to build the routing. And all this is kind of the same, right? Maybe our small network we talk about, we call that a track. Maybe this track is a bit more complex than what the .NET controller usually builds, but it's a scope. That's what it does. So we completely inherit this model. We live in this small world that goes overgrown now between the routing has computed this thing and there is a decision for this given packet. In our case, we don't use all the possibilities that the routing gives because there are too many of them. And we have to fine-tune how we use them, and for that we need to monitor the small network all the time at a very fine grain. So it's a direct inheritance from .NET. We also inherit from MANE, and we really hope that some people from MANE will come here. Now, we are not mobile. I mean, there is a big tension between mobility and determinism because it's very hard to solve a problem when it's fixed. Now, if everything's mobile, it becomes even harder. So there are people who can actually think that not only time, but also space are dimensions to the PCE, and that can be done. If you know deterministically where the objects will be, like these satellite networks, then you can start building deterministic path even over these many satellites in the air. Now, that's probably not the most usual case, but when the movements are deterministic, you can build a deterministic network. When the movement is not deterministic, it's just like when the flow is not deterministic, then you cannot build anything deterministic over it. So because of this tension with MANE, we can reuse some work, in particular things like DLIP. Looks fundamental and very interesting for us. But we have to think DLIP over multiple hop, not DLIP just between one router and its wireless interface. So we have to be able to collect all the DLIP information over multiple hops and feed that back to where the PSC decision is being made. CCamp, yes, we'll need data model, and we'll need to extend the wired data models to express those pareo functions that now we're capable of. IPPM, probably there will be a mix of in-band and out-of-band OAM to dynamically measure this very small network. Again, fast-paced, but very small network. That's why it's doable. So we're not talking about inter-domain pareo function. We are looking at enabling a few hops over one or a few technologies and bring the reliable and available characteristics that we're after. So we are talking about small networks here, small networks within bigger networks. And beer is also a candidate, and there is a drafted beer to actually place in the packet a source-routed decision of where replication should take place or where elimination should take place, etc. So what we need to do, we first need to check, obviously, that we have use cases and technologies. And like I said, there is a discussion on technology draft coming next. We'll see that more and more radio networks are coming with capabilities to schedule, meaning that we know that once Throw has completed all the work, we can actually couple multiple hubs of those different technologies and produce the ultimate goal, which is, the number of nines that you want with the loss that you want within a bounded latency. We don't claim we can do that on the first round of this working group, but that would be the ultimate goal. So we can work with source-routed, or we can work with distributed operation, and the group will have to define, what it wants to work on. So whether the decision, the PSC, is on the source, on the ingress of this network, and then all the OAM information has to be flooded back to this guy, or if actually there is some signaling in the packet which says down the path, which helps down the path figuring out how you make a distributed decision of using this redundancy that the network has given us. So we need to tag the packets with the decision, or if it's source-routed, or helpers to make this decision if it's not source-routing. And on the other hand, we'll have to do this BFD or OAM or IOAM or whatever else extension to get a picture of the current state of this graph at this very moment. So these are the two things that we really need to provide. Get the visibility on this very small network at a fast pace, and then provide the right signaling in the packets to use that, what's available wisely. And if I have time, I have a few experiments that I could share. I have 8 minutes. So let me just show you a few graphs. I hoped I would be able to, because I find them kind of interesting. So here is a small network, and these are real-world measurements, right? And we just artificially created some loss because those networks are actually quite reliable. So we had to force some errors to get there. But so you have an upper path in red and a lower path in blue, and the two pictures on the top show you basically the number of transmissions that it took for a given packet to get from A to H. So on the first two, we do normal IRQ over, so top left, top right, over a single path, meaning you try to send. If it doesn't work, you resend. If it doesn't work, you resend. So on the vertical, here it's one time. So you see that the packets that are on these lines, they made the whole path without a retry. The packets which are seen here, they made the whole path with one retry. It doesn't say which one. You just count the hops that it took for a given packet to get there. And you see that as you go, more and more packets, there are less and less packets which add more and more retries. For instance, you get a packet here. I don't see if you can see the blue dot. This packet experienced 15 transmissions. The more transmissions, the more spectrum, the more energy, blah. And now, does that translate into benefits if we actually do replication at the ingress, but no retry, which is this curve here? In this curve, we have scheduled every transmission. That's why we have an integral number of transmissions, always the same. So there are 10 transmissions to cover all this thing with replication and elimination. So that was a schedule with 10 transmissions. And obviously, all the packets that made it with exactly 10 transmissions. That's what we call bounded latency through scheduling. That's exactly that. Now, the packets which are coined -1 are the packets which never made it. We also count them. right? So you see that the number of packets never made it on this network, in particular this time because we placed an object in the middle, or we put away the antenna. I don't remember what we did, but we just prevented the transmission for a small amount of time. So basically, what does that tell us? First, this tells us that if you just have one path, you don't have a viability, right? Because you lost so many packets at this time. The network was not viable. You cannot build a safety network with that serial design. That's one thing. Second thing that, I need to turn here. So second thing that this tells us is compare those two curves. So the red path, the blue path, and the deterministic path. You realize that most of the time, hot potato does better latency than determinism. And that's actually a very classical result. If you look at TT Tech, the old presentation they made forever, they showed you this bell curve which never really ends compared to the spike of the deterministic traffic. So when you schedule stuff to deterministically deliver at a certain time, what is not deterministic is the amount of packets that are delivered, but you can deterministically say the packets will be delivered there or not. And so you see that actually the packets have a higher latency, which is not too good. You also see that in terms of loss, so this is the count of -1, so this is the count of loss. You realize that there are more loss on the red path because we did this interruption, but in a more normal network, sending the packet twice all over versus, even with some replication elimination here, versus doing the ARQ, actually the ARQ was more efficient. So if you just cared about reliability most of the time, you realize that a single path with ARQ is actually has better latency most of the time and is more reliable. So we're not necessarily talking, when we build this redundant path, we are not necessarily talking about improving the latency or improving the reliability. We are talking about a viability only. We are talking about safety applications. And the more safe you want to be, the more of those paths you're going to get. And the more energy you're going to waste, because you waste 10 energy units per packet. Here you just use 4. So you see that even in terms of energy, the replication elimination game is not as efficient for most packets as just sending a very single path and retries. What you really care when you build this is safety, right? And you realize that you're wasting energy and you're wasting time. So that 3 minutes, that's when you want to do better than that. And now you see the raw problem. The raw problem is, what can I do to get this green curve to the left, to get this blue curve down so that it matches pretty much something here? How to avoid the waste of energy and the waste of bandwidth that you can see here and still provide the viability that you care about. And I will not have time for both slides, but I can at least tell you what we can do for energy saving, just an example. So what we do here is, we have a draft at Beer, so feel free to visit that draft. And basically the Beer draft says, you put some bits in the packet to say which of those segments you're going to use. And when you do elimination, when you do transmission, you reset the bit on the hop that means the hop that you use. It's BRTE. On the other hand, when you do elimination, you end the bit mask that you got. If you think about it, that leads to the fact that when the packet arrives in the end, if a bit is not reset, it means that transmission failed. So now you can observe, if you set all the bits at the ingress, theoretically the packet should go through all the segments and all the bits should be reset. If the packet arrives with all bits set at the ingress, if the packet arrives at the egress with some bit not set, that's a map of what didn't work. So what you do is you send some packets with the full bit map, and that's the packet that you see here. All those packets took 16, 17, I can't read from here. No, it's 10, 12, 13, no, unit 11, I can't read. Units of energy and also units of time, because they went through all this path. But you see that most packets did not, because once we've done that, we have a map that we can use. So we just set the bit of the segments that we really want to use. When there's a loss, there is a signal back to the source saying, hey, in order to avoid 4 losses in a row, please set all the bits again, which increases a lot the reliability of your packet. And by doing this feedback, we can see that most of the packets take a minimal number of hops. Sometimes here we went around a certain problem by rerouting. and then back to the least energy path. I have 1 more minute, so I can just show you the result. So in dark green, that's when you do full replication. You realize that you have a better reliability. You get more packets through, but the cost of energy is twice. But because of the feedback loop, we can avoid the losses in a row, because you see there is never 4 losses in a row. So you see the gain by, this is just one method of tuning the use of the network so we consume less energy, and still we stay within the bounded latency, because we're still deterministically scheduled, and a number of loss in a row. That's just to illustrate that there are ways to achieve the row thing. And there is another slide if you care to look at it, and I won't have time for it. Question, Janos.
Hi, I'm Janos Farkas. A question first to the chairs before diving in. Do you want to have reflections and discussion now, or at the very end after all the presentations?
Yes, we have time for discussion later. So if there's some clarifying questions now, that we can take. So.
Okay. Well, I guess I have a longer comment. So maybe then should I come back during the discussion?
Yeah, that might be better to, if it's more open-ended, do it during the discussion.
Okay.
So Ganesh, are you ready to present remotely?
Yes.
Has everybody signed the blue sheets? There's one circling still back there somewhere, but and I have one here.
Please confirm if you can hear me.
Ganesh, if you can hear us, I think you have to click some sort of I wish to present button in your Meet Echo client. Until you do that, we can't do much from this end.
Yeah.
Yeah.
Let's give it a minute and see.
Can you hear me now?
Yeah.
Oh,
We can hear you, Ganesh. You have to ask to enter the queue, and then you get complete control at that point.
Into the virtual queue? Is that what it is?
Your volume is very low. Can you turn up your microphone? If there's somebody from Meet Echo on this, can they assist him?
Yeah, how about now? Is the volume better?
A little bit better. Can you go louder again?
Yeah, I can speak louder. Is that better?
That's much better. Thank you.
Okay. Am I in the queue now?
If just go ahead and shout next slide, and I will press the button for you.
Okay.
Ah, there. Hold on. Here you are.
Okay.
Yeah, you should have control.
I'm
now.
not seeing. Yeah, I'm not seeing my screen, my slides. So are you presenting the first one?
I'm showing the title slide now. Do you want the first slide? There you go. Page
No.
2.
Okay. Yeah, I'm not seeing which slide you're presenting.
Apparently, you
Okay.
have a slide button you can press on the
Yep,
on the
I got it.
client. Cool.
Okay. Thank you. I hope you can still hear me loud and clear. So following up on Pascal's introduction, I'm basically going to talk about how 802.11 can enable the goals that we have for reliable and available networks. Specifically, 802.11ax that's wrapping up now, and the new project 802.11be that's building on the features that 11ax has and adds more features that would enable us to be a viable medium for time-sensitive networking. Next slide, please. So the next couple of slides are basically slides that are introducing how 802.1 is structured and how it can exist in simultaneously with other 802 technologies like 802.1 and interoperate with multiple media at the same time. Can you go to the next slide, please? Okay, so this slide shows a feature of 802.11 called 802.11s. It's a mesh network that actually allows multiple 802.11 nodes to be connected to each other and establish paths, sometimes even redundant paths, to enable packets originating from one 802.11 node to reach the destined node by traversing across multiple 802.11 nodes. You may also hear multiple uses of the term mesh. There's one 802.11s, which is the standard mesh, but most implementations have diverged from the standard mesh and created their own proprietary versions. So the term mesh is a little bit non-standard at this point. Next slide, please. So this is a slide that has been around for quite a while. It talks about how 802.1 and 802.11 can coexist and extend the time-sensitive features of 802.1 to 802.11. That doesn't come automatically. There has to be a lot of work that needs to be done in the 802.11 domain. Some of them are already part of the standard, so we can leverage them, and some of them need to be worked on in future 802.11 projects. Some probably in coordination with the IETF RAW to ensure that the requirements that RAW comes up with are supplanted with features in 802.11. As Pascal mentioned before, the challenge with wireless is the link capacity is not constant and changes quite frequently because of interference and noise. And so the adjustments for reservations made end to end to cope with these with the changing capacity of the link is probably what we should try and address in order to be able to provide reliable and available service. Next slide, please. So this is a map of different 802.1 specifications that are already out there, and it tries to show you where 802.11 needs to do more work. For example, time synchronization, 802.11 already has a couple of protocols that can work with 802.1as and provide time synchronization in the wireless network. And the same is true of interoperating with 802.1. We have 802.11 AA that provides the stream reservation protocol that ensures that you can make a reservation from end to end. And also 802.11 AK that provides bridging feature for 802.11 networks. For bounded low latency, we have some features in 11AX, but that they may not satisfy all requirements. And some extensions are being worked on in 11BE that provides bounded low latency. And the same is true for ultra reliability. We do have some reliability coming out of 11AX that can be improved by new features that have been discussed in 11BE. So what we try to show here is that we have a bunch of 802.1 TSN standards, and there's already work being done and incorporated in the .11 standard that can work together with .1, and there's already work going on in the current projects that will further enable 802.11 to be a good participant in a time-sensitive network. Next slide, please. This is a slide showing what we can do with what we have with 11AX at this point. 11AX is also known as Wi-Fi 6. So in 11AX and all other standards going forward, we have this notion of a scheduled operation where the AP has total control over the medium for all the stations that are associated with the AP. And if the stations have already indicated the type of traffic that they anticipate, the AP can schedule transmission times for each of the stations, thereby reducing or eliminating any need for backoff. And if you can eliminate backoff, you'll eliminate all dead dead time in the air and maximize the use of the spectrum to send traffic that is critical. In addition to that, we also have other mechanisms, QoS mechanisms built into 802.11, where we can prioritize time-sensitive traffic over non-time sensitive traffic and make sure that any queued time-sensitive traffic gets the first chance to get out of the device. So we did some simulation based on 802.11 mechanisms. And the chart on the right-hand side basically shows you that the lower the latency that you want, the less number of stations is what you can serve given a specific, given a constant bandwidth. So if you want to serve more stations with the same bandwidth, then you will have to relax on the latency, given the same number of reliability. So here we are talking about 5 nines reliability. But this is definitely achievable with 20 megahertz bandwidth in 802.11. You can serve up to 45 stations if you use the 802.11ax protocol. If your bounded latency requirement is 3 milliseconds or less. If you want tighter latency, then you'll have to sacrifice the number of stations that you can serve. Next slide, please. So this is the 802.11be is the new project that we are currently working on in 802.11. And it's building on 802.11ax and trying to bring in other techniques to make the medium more available and be more sensitive to traffic that's time critical as opposed to which is not time critical. So first off, as we do in most of the 802.11 projects, there are enhancements in better coding techniques, using more spatial streams, using wider channels, and thereby achieving a higher throughput. So this is just sheer throughput that you can, we can go up to 2 gigabits per second with these enhancements. In addition to that, we're looking at techniques where the same station can operate in 2.45 and potentially 6 to 7 gigahertz spectrum, so that you have multiple links between two devices. And you can leverage the fact that if one link becomes noisy, then you can route the traffic through another link. They are all 802.11 links. They are not different technologies, but they're the same link operating in different, same technology operating in different bands. And the third one is trying to coordinate and leverage multiple APs that are within radio range of a transmitter and see how we can improve reliability by using multiple APs to route the traffic from one device to another device. And Pascal already mentioned the use of hybrid ARQ. Some mechanisms for using hybrid ARQ are being talked about in 11be as well. And the last one is to provide a new mechanism where channel access to time-aware traffic is prioritized over non-time sensitive traffic, thereby ensuring that egress of time-sensitive traffic happens first if it happens to be queued at the same time when non-time sensitive traffic is also queued in the same device. So all these mechanisms are being debated right now. They are not completed. They're in various phases of being specified. But our hope is by the time we make progress in RAW, we can bring in more requirements from RAW into this project and make sure that 802.11 satisfies all the requirements to provide a wireless network that is reliable and available. Next slide, please. Okay, so this is a summary of all the things that we talked about. I already mentioned that 802.11x provides a new mechanism where latency and reliability can be controlled and achieved compared to what we used to do in the features that were before 11ax, 11ac, 11n, and lower. 802.11ax and 11be will also operate in 6 to 7 gigahertz band wherever it's available. It's not universally available yet. With that, we have more spectrum, which means we can combine multiple channels together and go up to 320 megahertz channels that are 320 megahertz wide. That gives us more opportunity to send smaller packets in a shorter time, and that way achieve lower latency or higher reliability. And 802.11b is actually a natural progression from where we are, where we finished in 11ax, and where we want to go beyond that. And this is a good opportunity for us to inject features from requirements from raw into 802.11.
Thank you, Ganesh. If you just hold there a second, we've got a couple of
Sure.
questions on the microphone. Yes.
Sure.
Hi, Ganesh. Juan Carlos here from Sigfox. Just a quick question on, so is the BE Mac planning to use different PHYs or just the 6-7 gigahertz one?
From what I know, it's not a different PHY. It's just the 5 gigahertz PHY that can also work in 6 to 7 gigahertz.
Okay. Okay, thank you.
Janos Farkas. Hi, Ganesh. Thank you for the summary. I would just like to highlight one point and reiterate what Ganesh mentioned already, that there is a work ongoing in 802 for the integration of TSN and .11. And if we do a good job, one way to look at it, that we get an 802 LAN including wireless LAN and wireline components, that is the subnet technology, or can be used as a subnet for that net, like a seamless fashion.
Thank you.
Thank you very much, Ganesh. We'll move on to the next presenter.
Sure.
I think he got a good tip, but I kicked him.
So actually, we get a draft to help the IETF user discover this technology and other technologies. So we have. So actually, we have at least 4 technologies which are already discussed in the draft. Well, actually, 5G is a bit late, but we have text from Dave and Ganesh about the extensions of Wi-Fi from Wi-Fi 6 beyond. We've got 1540 ACH, which was used the IETF for 6-dish. And we have also a text on LDAX, which is an avionics technology for air-to-air and air-to-ground deterministic transmissions. And so basically what we want to illustrate here is that we are not trying to solve prime on links which don't exist, but there are actually multiple efforts in multiple domains where the raw technology can become useful. And basically what we're after now is a layer 3 abstractions which allow us to couple those things and build a network which is a composite of different technologies. So we have Niels here who actually participates in the development of LDAX. So if you could tell us a few words about LDAX.
Yeah, hello everyone. This is Niels Maurer from the German Aerospace Center. So let me briefly talk a little bit about what's going on in the communication section for aeronautical communication. So everyone using a plane today mainly relies on analog voice communication for safety relevant communication. This is currently changing. So there's a future communication infrastructure coming up there are several technologies discussed, such as Aeromax for airport communications, LDAX for terrestrial air-ground communication, also air-to-air communication, and satellite communication for oceanic, polar, and remote regions. So we have a multi-link system. Via multiple hops, data needs to travel finally to the aircraft. And so we from the German Aerospace Center have been working for 15 years now on LDAX. So the most important part to understand here is data travels via different technologies, via different hops, and needs to reach the end user, so the aircraft, in a certain amount of time reliably. And this is why we think RAW is very important here for our work, and we can contribute with that technology.
So many thanks, Niels. So we have actually uploaded a set of slides which won't be presented today that came from Niels. And so if you go through to the agenda and the list of documents that are available with the agenda, you will find actually some slides on LDAX. There is also a separate document which is published to the RAW list of documents, and that is specific to LDAX. So you have both the section on LDAX in the technology document plus a separate document on LDAX. Many thanks.
Do you want to talk about the draft, or since
Well, that's what.
no? But sorry, the other drafts.
Oh,
I
I thought
you're done.
later. No?
Yeah, but it's up. It's right after this.
You do it now.
Well, if you have the slide, I can.
Yeah, it's part of the chair slides.
Out of the chair slides.
No?
So any questions on this? As Pascal said, there is some additional slides if people want to find out more about the LDAX side of things. So.
Is it the intro slides?
No, the chair slides.
Well, maybe we do it later.
No, it's the next thing that's up. Go down. Draft discussion. Let's start with the draft.
I've got it open already.
Yes.
So it's straight up to you.
Okay, can you? Oh, yes. I'm not sure to should. Okay, so just to illustrate, there's quite a bit of work which has already started through the RAW mailing list. And so we've got all those documents which are already available. We've got, so Carlos presented the use cases. So there is a full draft with many use cases in there. We've got the technology draft that I just discussed about, and we'll publish more on 5G very soon. And I don't know, maybe we'll also include Bluetooth, because there are interesting work. There is interesting work for raw properties over Bluetooth Low Energy. We've got the draft by Niels about the LDAX. So that's all the generic information about the lower layer that we can use for raw. Then we've got the prime statement that I presented. We've got a requirement document by Georgios. No time today to present it, but it's quite interesting, so please go through it. And we have a beginning requirement document for the kind of OEM information that we'd like to get to be able to measure this particular small network that we're building, that the routing is building for us. Not surprisingly, the work at RAW is expected to span, to trigger some work in other working group where the specialists to solve a particular problem are. We already have a draft which is actually in the solution space for RAW, which is being pushed at RAW for enabling a complex track using REPL. And we also have a BRT draft at BEER. So the goal is, yes, we inherit from Manet, we inherit from .NET. We understand our prime because we realize people, but the solutions are not necessarily to be built within RAW. Once we can express the prime, then we can go to a particular working group and work with the experts of that working group to actually solve that component that RAW needs. That's how we see the work, and it has already started.
Okay. Thank you, Pascal. No, it's us.
Oh, it's us.
No, it's us. No, you just continue. I put them all
Oh,
together.
you put them all together.
So, time to get into the discussion and the charter. So let me talk for a few minutes. So both of us as chairs haven't been involved in this work. So we sort of came in new to this, well, starting about a month ago. And we said, okay, what is this? Can you explain it to us? And as we were discussing, we sort of came up with, well, this was the most complex, simplest picture that we could come up with, saying this is how actually is what Rob brings to the table is this notion that you have various paths that are computed by a PCE somewhere. And you might get some metrics from some existing ways of measuring metrics of different radios, and then you need to be able to select as you forward packets, where am I going to send things this millisecond, right? As opposed to next millisecond when something might have changed. So that was our very sort of simplistic understanding of what we're trying to do here, and sort of like we haven't done this path selection engine type thing anywhere else in the past. We've assumed that you can compute these paths and they stay stable for the time scale of routing. So this was what Pascal was talking about earlier. So that was sort of us as chairs trying to understand, what's the big picture here of how this stuff fits in. And next, before we get into the discussion, I will pull up parts of the proposed charter. So you can go read this stuff yourself. There's 3 pages here of background text giving the context, which is what we talked about during the BOF today. And then the key thing that I would like to leave up here is the set of proposed charter work items. So now the floor is open for discussion, whether it's about the work items, whether it's about understanding the problem statement and scope of the stuff. So, floor is yours.
Hi, Lou Berger. Can you go back one slide? There, that one. Thanks. I guess you skipped over a bunch. I jumped up when I heard you say we've never done this path selection thing. So as I understand it, there's a couple of different aspects to the problem. One of the things you're trying to do is to do a fast forwarding decision, right? One problem is a better informed path computation based on what's happening at the RF layer. That's not this one. This is, you want to do a better forwarding decision based on what's happening at the RF layer. We do all sorts of forwarding decisions in the IETF based on all sorts of information from the link layer. So saying we've never done that before, I think is a huge overstatement.
Yeah, this is the chair's poor understanding of this space. So let me preface it by that again. But yes, as you say it, I say, oh yeah, fast reroute type stuff. Yeah, we do lots of that type of thing.
And ECMP is a form of it too, right?
Sure.
In DetNet, we do pre-auth, which is we do a nailed up version. In the DetNet definition, there's allowance for other forms, like exactly this one, whether it be network coding or, as Pascal said, or something that we previously haven't talked about, which is maybe doing a forwarding decision based on the RF layer telling you which of your available links are have higher probability of delivery. That is something that's new. But this type of thing, we have a long history doing in the IETF, and we even have working groups that fits in its charter.
Okay, yeah, so we were a bit confused, or at least I was confused in terms of not having done this before. So sorry about that.
Following on from that, Rick Taylor here, following on from that point, Lou, there were lots of we could, we might, particularly concerning work in DetNet. The reality, as I understand it, is that DetNet has plenty of work to do and isn't hugely interested in looking at this fairly niche case from their perspective of wireless networks. And part of this BOF is trying to determine whether there is sufficient interest to do this work in a working group of its own, or whether everyone who is interested here goes and sits in the back of DetNet and takes and does that work in that group, or MANE, or elsewhere.
CCAMP would be.
Or CCAMP. I mean, is CCAMP so light on work, and does CCAMP have the interest to do this work? That is one of those open questions.
Yeah, it's a reasonable question. In terms of the point about DetNet being overloaded, we're wrapping up the core forwarding plane documents, by the way, which includes the protection mechanism of pre-auth. And maybe we have a new protection mechanism that comes in that could be applicable to multiple technologies, because there's no reason why you have to limit the, PARO. I don't remember the new acronym. You don't necessarily have to limit that just to wireless networks. That could see applicability elsewhere. So do we have time? Well, we're wrapping up and probably going to do rechartering at the next IETF. So maybe there's time there. Is it the right place? That's a different question. And CCAMP has historically done where we have the layered network model and doing traffic engineering over different layers. CCAMP has been the home for that. You do end up in those groups having a set of people that sit around board while they're optical people. They really don't care about hearing about microwaves, and vice versa. So you have some people sitting around. Is that the right? Where's the right place? I don't know. That's not really my call. That's more for the ADs.
Just to add to that, Pascal made it abundantly clear that a lot of these problems do inherit from DetNet. So there's, we're not claiming this is new and unique in that sort of, there's a parental relationship there.
Okay, so there are two aspects to this. The first aspect is we care to receive in this group, if we form it, a crowd which is widely interested and specialized in wireless primes to make sure that those wireless primes are really considered. And the type of discussion that have happened so far at DetNet would not attract that kind of crowd. So if we kind of plan to do it within DetNet and would want to avoid boring people in the room, half of the population, the wireless or the wired half, then we would end up in doing like 2 sessions. We would have the wireless session and the wired session. And so in the end, I mean, we could also do a single working group for the whole IETF, but I think that the whole idea of splitting things into domains and areas and working groups, as opposed to having one big working group meeting the whole week, as other entities do, right? I mean, I'm not saying it's wrong, is that we can actually focus on one particular thing. And then what's great is we can actually interact with the other working groups, and Ro will certainly interact a lot with DetNet, and could even be pushing some, extensions to some models that DetNet or CCAMP are actually defining, so that we're sure that the raw requirements are being served. Doesn't mean that everything has to be handled at raw, but it means that the congregation of people that would be meeting would actually have its own space to discuss, and within a group of people who understand each other, use the same term, and talk about the same thing. So that's just to make the meetings more useful. The other thing is I was there from inception in DetNet, and I really helped create it, I hope. And it was my goal 2-3 years ago to get this sort of discussion within DetNet. And I pushed and pushed and been there and tried, and the bottom line, you have seen the word wireless come in, go away, just like a wireless link does, because that was never really the interest of the people in the room. I was pretty much the only one interested. I'm exaggerating, but never managed to get focus or attention on wireless. And you can understand why, right? There are very interesting problems to be solved in DetNet in many areas. And you see what the work is at this moment. That gives you an idea of what the focus and what the people are, who the people are in this room. That's perfectly good. It's just that if you try to attract radio people in that same room and you hear those discussions, you say, hey, why I'm here? I mean, what I'm doing here, right?
So this is a discussion we've had before many times in the traffic engineering world and in the CCAMP context, where you have lots of different technologies where we're trying to apply the internet control plane, the IETF control plane, to all different types of switching that apparently have very little to do with each other. And the fundamental question is do we want to develop single sets of mechanisms that are tailored to particular environments, or do we want to develop a common tool set that can be run over multiple network technologies? And what we've done before, at least in the routing area, and I'm particularly talking about CCAMP and TEAS, is try to identify what's common across different technologies so that we can apply internet technologies no matter what we're transmitting over, whether it be light, RF, traditional wires. We want to have a more commonality than not commonality. And I think that's the question for the ADs and for the group is, do we want to try to come up with tailored solutions for wireless, or do we want to come up with a solution that uses as much common mechanisms across different technologies?
So,
by the way, from an interest standpoint, in DetNet, we've had people that have been interested in wireless from the start. And example, there were some aircraft folks who early on, it's been mentioned many times, and it's always been, let's finish the core technology first and then start working on the next one. So the core technology, we're pretty much done. We're just finished last call. The first layer of technology adaptation, so mapping DetNet to TSN, that's coming along really nicely. There's opportunity to bring in the next technology. I'm not saying that that's the right place. I think that's, for others to decide.
Understood.
Janos Farkas. So first, thank you for the problem statement draft. I think that was a step forward compared to previous IETF. It is still not clear to me, although. So trying to lay out a train of thoughts for that. This comes from .NET in the sense of what is the ultimate goal? To provide deterministic networking in combined networks of wireless and wireline deployments. I fully agree that we should do this, and I have the feeling that there are gaps that we have to fill in. So I fully agree with the ultimate goal that we should figure out what to do, what are the gaps, and fill the gaps. So my understanding, that's the ultimate goal, what we are discussing. Thinking it further, based on the layouts of the problem statement, it goes into the, .NET distinguishes two sublayers, service and forwarding sublayer. And this is a particular lower layer in the forwarding sublayer in my understanding. So the gap analysis could be, as we started in the core technology data plane, what is missing in the .NET forwarding sublayer, what is really needed to be done in support of various wireless technologies. And with that top-down approach, that could be done in .NET in the next phase. So wireless has been in scope from start. It's been in the use cases, and we want to solve it. Reading the problem statement draft, to me, it was kind of an extension to 60s, really. So it was not a generic, let's cover many wireless technologies. There is the track, this directed acyclic graph, and so on. So my understanding, it was extension of 60s. Did not take into account license spectrum at all, which has better scheduling and so on, different perspective. And from the bottom up, yes, sure, something needs to be done for 60s, but maybe it's different for the different technologies. Furthermore, the kind of APIs I read as necessary from the problem statement are not really supported from the wireless technologies. This is where DLab can help, and it was good to see that picture to expose the necessary data. But my understanding, neither .11 or 5G provides the APIs that are needed for the layout of the next selection in the forwarding sublayer. I don't see, for example, how from layer 3 we could influence the arc of 5G. So this is a gray area. And from what I also, and this is the last sentence and I finish, what I also mentioned before, from 802 LAN technologies, it is happening, the integration is happening, so we will have some kind of subnet, an 802 subnet. When it comes to 5G TSN integration is happening, so we can, if somebody wants to use 5G as radio, it would be possible to, thinking of the .NET architecture, replace the TSN subnet with the heterogeneous wireless and wireline with two aspects. And you had sent on the list a nice picture of your whiteboarding, which you sent to the list a nice picture. You drew something on a whiteboard and sent a picture, which actually plays RAW as a subnet technology. Yep. So I would do it top down, start from .NET and figure out which group, CCamp, which group should do what.
So can I just jump in at this point with a quick question to the room, because I'm really pleased to see there are lots of people in here, and that might be because scheduling happenstance, or it might be that people are genuinely interested in this subject. How many people here are intending to go and actively join in the .NET working group meetings tomorrow? Okay, so that's, in my opinion, under half of you. So take that, make of that as you wish, but as we talk about, does this work live in .NET? There are people here who aren't going to DetNet. I'm not sure that's statistically significant in any way, but it's worth thinking about. Carry on.
But it could be that the other half, Michael here, Richardson, it could be that the other people aren't going to DetNet because DetNet's not working on the topic.
Exactly.
Right. So,
Yeah.
but that's chicken and egg problem I think you have there. Right.
Yeah, I mean, I think that
I'm not going to DetNet because it's conflicted.
but I mean, I think that there's two things, right? One is do people find, is it clear what RAW is proposing to do here in terms of the problem statement, the proposed work items, etc. Right? Then there's a separate thing about, and do people want to work on that, etc. Which is questions we will ask shortly as we have discussed more about this stuff. And then there's a separate question about, okay, where do we place those work items, right? Is it a separate working group where we have a separate community of people, potentially new people coming in with more radio expertise, or does it get folded into some existing working group? And I think it's, as Lou said, I think it's up to the ADs to decide that stuff. But I think the key thing from sort of understanding what's being proposed is the clarity about this stuff, right? Do people understand it? Is it well scoped enough? So anyhow, continue the discussion, please. Yes.
Stu Card. I've been doing internet protocol-based airborne networking for about 25 years. And I have noticed that we, as a community, have left the field of airborne networking to the builders of radios, who know at best how to build data links, not networks. There have been a couple of notable exceptions where the IETF has indeed contributed to airborne networking, but they have been by and large notable exceptions. Airborne networking faces unique challenges. And I realize this is not all about airborne networking, but the LDAX example was listed. Sometimes a niche, even if it is small, requires a home where people who are focused on those unique challenges can address them.
Ning Zhong from Huawei. I think good work. I think in general, I think this is interesting, especially on the problem space. But I still would like to see architecture to highlight how this work actually can interact with other components like .NET and things more detailed. Because I can see that the purpose is to propose based on charter, to propose some L3 abstraction to enable, some, the work and how to, how to do such kind of interaction and benefits the L3 end-to-end service guarantee or something. But I saw some text, but I never see the architecture, which I think that maybe make it more clear. And without such kind of detailed architecture, it's really difficult for me to, agree on this charter or do some new work in a new working group or in existing work. So I'd like to see that. Thank you.
So clarifying question. Yeah. So you're saying that what has been presented today, you would have liked to see an architecture in more detail, as opposed to one of the future work items should be writing down the architecture?
Well, it's not necessary to be a new work item, but I would like to see some architecture. Maybe it's better to present, or discuss on the list or something. Yeah.
Okay.
Luberger, I think we can narrow the discussion a little bit on the choice for the room for the ADs. I would assume we're not going to go sort of take on the work of the radio layer guys who own those PHYs. We're not going to do that. We probably don't want to have two groups doing the same thing, like defining protection layers for .NET. That'll probably go over to .NET. That's pretty clear. There's maybe some things that DLEP enhancements probably is going to continue in MAN-A, wouldn't come into this group. So what's really left? It's the architecture. It's sort of the framework. It's sort of understanding how to apply it to a different environment. That's something that a small group of people or a focus group of people can go do. And whether you do it in the a new working group or as a group within a larger working group, as long as the work's getting done, that's the most important thing. So I think, you can focus it down to that architecture, framework, solution approach, that overall picture, and then just decide where, number one, if people want to do that, and personally, I hope they do, and then number two is where.
So, Rick again, as I understand it, Pascal and the other guys who've been working on this and got it as a BOF at Montreal and now here, I see, as I understand it, they are asking the IETF to help give them some structure and some more formal forum in order to have this discussion. So yeah, this could all happen inside meetings. This could all happen away from the IETF, but my understanding is that they have come with a request for, please give us a home to do this.
Tim Costello from BT. The good presentations and support the work here in this. My question is, talking about downstreaming or putting work into other working groups, but a lot of that was referenced the DetNet group. But would you also consider work going into working groups such as the QUIC and that to adapt the protocols to make them more wireless friendly?
I would say one of the great difficulties you have with defining working group charters is ensuring that the work is achievable and scopable. And although that idea is admirable, I think it's so far out on the periphery of what we should attempt to do. But if 101 people come to the mic and say, we want to go do this, then that's an entirely valid discussion, but I probably don't think that's raw.
Thank you.
János Farkas, just a reflection on the architecture. I think it would be not helpful to see a new architecture coming out of it. My understanding is that this should fit into the DetNet architecture.
Yeah, and this is Fat Tai Zhang from Huawei. So firstly, I agree that architectural framework stuff first is very important. So could you move back to the page 4? So yeah, regarding the terminology PSE, I'm not sure if this terminology is accurate or not, but it's a little bit confusing about the relationship between the PCE and PSE. I'm not sure if PCE should be involved in the law or not. Actually, in the problem presentation slides, it was mentioned that PCE is out of the scope of the law. So if PCE is not involved, I don't know how the PSE can get the past information to be modified. So this is the comment. Another comment is that in the problem statement presentation slides, there's a comparison table. So I'm not sure, I don't think that all the comparison assumptions are correct. For example, for the time scale, it says that for the PCE it needs much longer time to do the past computation. But right now there are more people, they are trying to use the PCE or controller to do the centralized restoration. So I think for the PCE it should be also very fast. Yeah, thank you.
So a little bit of clarification in response. This diagram is talking about logical blocks. So these are functions. It doesn't mean that they're not co-located, and it doesn't strictly define responsibility. It's more of a whiteboard rough diagram to talk about there is a selection function that must occur that works at a different time scale to the global path computation function. How that is actually manifested, or whether it actually exists as a thing, is something that can be discussed in any potential work that comes out of RAW. So,
yeah. One other thing I was going to add is that the time scale also has to take into account what's the quality of the links that you're running over. So you can clearly run a centralized compute, path computation element if you have lots of bandwidth and very little drops that could do things very quickly. right? Because it's just limited by compute. If you're running over somewhat unreliable wireless link at varying speeds over a large network, that might not be feasible at all. You might only be able to calculate these things every few seconds, and you want to react to radio changes that happen, you know, in fractions of seconds. So there are very different timescales, particularly when you take those radio aspects and reliability aspects into account.
David Black, could we get the work items back up on the screen? I'm sorry. Yeah, well, it did say being asked for. So, among the things I do is I'm the transport air advisor to the DetNet working group. As I look at these work items, I think the first two and the last two have a real strong difference in terms of how they relate to DetNet. The first two, a couple of informational documents to describe what is wireless and why is it different and how is it different. How does it force you to think differently about deterministic networking? That's stuff that can go on relatively independent. However, the second two, which is effectively an OAM document and a replication related redundancy control protocol, are going to have real strong overlaps with what DetNet does or could do or should be doing. And I wonder about sort of chartering those two independent of what is going of what is going on in DetNet, because we sure as heck don't need two unrelated protocols in those spaces, one to solve the problem for wired, one to solve the problem for wireless.
I guess one question for the room, me not being a DetNet expert, is there's a notion of being able to do DetNet extensions that don't actually change the DetNet architecture, but fill in some pieces, and being able to do that in a focus group that's not DetNet itself, right? As opposed to it needs to be done in the group. To make it easier to invite a different community that can focus on the wireless problems. But did that question make sense? I was rambling. We don't want to have a different architecture here, right? We want to use the DetNet architecture, but figure out to add the missing pieces to support these wireless use cases. And is it feasible to do that, open-ended question, without being in the DetNet group itself and feeding the work into DetNet somehow?
Hi, it's Lou. For those who don't know, I'm a DetNet co-chair. With respect to the architecture, I think you fit right in. You know, I don't have a problem with the boxology. As Rick said, this was just concepts. And I think you can directly apply that box. Where's Fatai? Lost him. That box goes into the service layer. We have one solution today. We've talked about other solutions for providing reliability over different network technology. So that last piece, what is that, number 4, doing a different way of doing redundancy fits right into that architecture perfectly. And personally, I think it fits right into the scope of the working group, and you can go do it there. All you have to do is bring a proposal, bring a draft, we'll talk about it. The OEM one, David was right on. We're in the process, OEM is trailing behind. We have pretty good handle on what we're doing for MPLS OEM. We don't have a good handle on IP OEM. You actually could help us solve our problem. And by the way, DetNet is not wireline. DetNet is DetNet, just like IP is not wireless or wireline. It goes over any network. That's what we're aiming to do with DetNet. Maybe we can have one OEM solution, not one for wireless and one for wired, but just one. So please come. I mean, I think we should do this work. That particular one, I don't think should be separate. That one, let's have one answer, not multiple answers.
Okay, so as a quick follow-up from that, Rick again. We've never had the intention of carving out our own little empire or, a raw, isolated working group. It's always about interaction with other people, definitely DetNet, because as has been repeated many times, there's so many similarities and there's a direct inheritance. My question to Lou is, if we turned up with all those drafts, and I won't find the slide, but there's about 9, and said, okay, we want to work on all of these, and here are all of these guys, and I'm looking at guys and girls in the room here. If we all turn up en masse into DetNet and say, we want to work on this, how disruptive is that going to be to your working group? And that's a genuine question.
Sure. So I think items 3 and 4 are completely complementary. So that's like a no-brainer. 1 and 2, if there's a group that really wants to talk about that in DetNet, well, I think we'll accommodate them. If we want to have that run as a small focused working group, I think that's okay too. As I said earlier, it's about getting the work done. And I also not getting competing solutions. I'm a big fan of having commonality. I mean, that's what IP is all about. And sorry, I have that religion. So, I think that would be dangerous, not helpful to have multiple solutions in the same space. But in terms of the focus of the discussions, do it separate, together. We'll have to coordinate either way. I think there's going to be a set of us that are going to go to both meetings no matter what. So, the fact that Pascal was talking about people not showing up and people having to go to multiple meetings, we're going to do that anyway. It's not a big deal. That's why we still meet in person, by the way.
Yeah. So I've heard a lot about this, like, where do we do work and, existing working group or new one and so on. I didn't really come to talk about that, but rather to suggest that there might be a opportunity to change the topic slightly. So I'm mostly interested in like how much sort of market demand there is for this kind of suggested functionality, no matter where that's being done. And I think that would be a worthwhile thing to try and get people to comment on. And to start off, my personal view on this is kind of like mixed a little bit, because clearly there seems to be demand for this, overall, like, low latency, critical communications type of functionality in the world. And, factories switching to new types of communication tools and so forth. And evidence for that is like the work at IEEE that we just heard about, the work at 3GPP and 5G and many other places. There's sort of layer 2 capabilities being manufactured to do that sort of service. But I think the question is not about the overall market, really. It's about like the delta that we at IETF would provide. And certainly we need to somehow take into account what's happening at layer 2. But the question in my mind, at least, is how much, like, are we happy with what we have, happy with what DetNet was already about to do? Are we going to create a big system on top? And there, I think, lies maybe the question mark. And if you look at way things are built, then there's a of course the question of, do you do things at layer 3 or layer 2? And it seems to me that the kinds of things that are being talked about here are most suitable for sort of the extreme situation of you have a mesh type network or multi-hop network, and possibly multiple standards, and then sort of the IP is the only way to get that done. But it's many of the deployments that I'm seeing are more like single technology on IEEE or other types of networks, and then the radio could actually at that level do things. And if you compare the sort of fundamental things that you can do at layer 3, like, well, the packet got through and didn't get through, whereas on radio you have like this 64 element antennas that you can measure like every beam exactly. And so when you make a selection at layer 2, you're sort of fundamentally tweaking the physics, that you're quite aware of what's going on. And at layer 3, in comparison, maybe there's a bit of a extreme comparison, but it's like shooting in the dark. You don't really know, like it's just on-off kind of thing. And to me, that speaks, maybe more in favor of relatively small amount of work at the IETF, and make sure that we can detect things that are broken and are working, and leaving the radio layer to do its job, because it does have all the tools available to it to figure out what's actually going on.
So, Rick, in quick response to that, the discussion prior to this actual BOF was understanding that this is this an IETF problem? And the answer I have heard from the active participants is the discussion is about building reliable wireless aware networks across multiple wireless link technologies. So sure, if it's an entire radio network running a single link layer technology, there isn't an IETF problem to solve there. But if you're connecting your multiple heterogeneous wireless technologies together to make a full path and requiring some reliability or availability constraints across those, then that is an IETF problem.
Yeah, I absolutely understood, but I was trying to move to the discussion of how much demand is there for that particular thing in the marketplace.
Can I quickly answer? I'm Rick Taylor. I work for Airbus. There's a reason I'm sat here, not just because I like helping the IETF. This is important in the aircraft industry and also terrestrial.
Thomas Gorbel, yeah, I was just I'm supporting you in that. My background is actually airborne radio networks, so I'm one of the guys building the radios for the airborne networks. And I think the room is maybe not aware of that, but basically I live in a parallel universe. We have a whole set of standardization bodies in the airborne industry that standardize airborne internetworking. And I say internetworking because we still use OSI protocols, if anybody here is still aware of what that actually is. And part of our difficulty to going to multi-homed, diverse IP version 6 mobile networks is that we have difficulty to find people to talk to in the IETF. So having a working group that gives us structure and people to talk to would greatly help us.
So Pascal Hubert, there's also a reason why I'm here, and we build products, and we have field problems with those products. And even if they are single type radios, actually now we are introducing multiple 5-speed, so it already creates some new sort of trouble. We have this exact problem that within this single technology, we have to build multi-hop routing. And we do that at layer 3 because we found that the layer 3 technology applied quite well to our use cases. So we did not rely on layer 2 meshes, but we do layer 3 meshes. And one hop can do the best, even if it had 64 antennas in one array to optimize that transmission.
Excuse me, just a quick time check. So we want to ask a few questions, but be brief at the microphone and let's close the microphone line. So.
Okay, so the bottom line is we need this technology in our current product line. And we have customer requirements that are associated to that. In real products, that's not avionics, that's smart grid. So just to enable automation within a smart grid, people invest a lot in those networks. Right now, they use them for AMI, but they find that considering the investment, they want more services from those networks. So now they want more capabilities from the network, and basically those capabilities are related to automation, and they want raw.
Yeah, just Niels Maurer here again. So one really quick comment about bringing new people to the IETF, why wireless is important to do that. So the difference is here, you need to do good channel measurements in order to understand your wireless channel. And this is becoming ever more important with the advent of UAVs coming in, autonomous flying and so on. So you need to be very exact in how the information actually travels. So I think RAW is a very good opportunity to bring in a whole new bunch of people in with different background to do the channel measurement, for instance, in this working group. Thank you.
My name is Umar. Just a comment here. I see the problem laid out here is a little bit different than what DetNet is doing, for sure, especially for the 0.4. You guys are seeking, for the timescale issue, you guys are seeking to put in-band signaling. So I didn't hear which data plane. You guys, so I see BTE is one data plane, but it's not sure you are seeking to create new data planes. But I see this is a new thing, in-band signaling. There's a one in-band signaling stuff that was being presented in TSV working group using IPv6 extension headers. But I see this is a new thing which is not done in DetNet. That's my comment.
So let's try to get some hum. So not about necessarily where we place this work. Well, maybe there will be a question about 4-meeting working group. Sorry, but first of all, do people in the room please hum? I will ask yes or no. We'll ask both of these questions as one question, and we can split them apart if we need to. But if you feel that the problem statement has been stated is sufficiently clear and well scoped, then the work items as stated in the that we've had up here, the 4 items. If they're sufficiently clear, please hum. If you feel that they're not sufficiently clear and well scoped, please hum. So I hear some hums. Clearly, most of them hummed for that they are clear and scope, but there was a few for the second one as well. Does solving this problem belong in the IETF? Please hum. Does solving this problem not belong in the IETF, but somewhere else? Is that background noise from the fans, or is there some other? What, is an aircraft flying over? Is there support for forming a separate working group as presented, discussed work items in this charter? Please hum. Is there not support for forming it? Whatever the opposite, please hum. Yeah, that one, I sort of expected that based on the discussion we had leading up to this stuff, so not surprising. So 50-50 approximately from the volume over here. So.
But a lot of abstention. That was quite a quiet hum on both sides that time. So.
Hello, it's Deborah, the 80. Can you go back to that slide here? Okay, so I heard a lot of concern. There were 4 items, right, for the work items, and the first 2 were informational. The third and fourth were more protocol, which questionable if it really should be DetNet or what. So if it was only those first 2 items, let's take the poll, because we have a lot of working groups that are done with the very limited scope, right, to do something very fast and then merge back into other working groups. So if it was only the first 2 items, those informationals, can you just do the poll again?
Yep, definitely that. So those first 2 items, is there support for forming a working group with those 2 work items in the charter? Please hum. Is there any opposition to doing that? Please hum. That one was, yes, quite different, right? So it was not completely quiet on the second one. But what? No, I said it was not completely quiet on the opposed one, but it was not volume things. I would say it was like 80-20, 90-10 type thing as opposed to 50-50. So, and then, you know, who in this room are planning if we chartered, yes?
Just a quick comment, because I was the one who was humming against on the latest one, and that the reason for that was not sufficiently interesting enough. Like, if you only do the 2 things, then, you know, why bother?
Yeah, there's a separate question which I'm going to ask Deborah about, which is, I thought the ISG didn't want to charter things that only do like informational documents, but we'll do that afterwards and figure this out.
There was the gentleman who explained that the problem does not exist because the PC is fast enough. And yes, at some point, I mean, for many DetNet deployments, I mean, we can live with just the PC and the network without a PSC.
Sure.
The PSC is really the piece that is an extension to DetNet, an overgrown piece of the architecture that does not even show on the architecture as written today, because in many ways, deployment is not needed at all. And so the other way of presenting this work is to say, hey, what if DetNet delegates this work to row and does not try to do the competing solution, just since it's a very particular side effect of DetNet, which only appears in a particular types of use cases, some people being not interested at all.
Let's finish asking the questions. We have about 2 minutes left. So
the question was interesting in forming it as long as it does not compete with DetNet, because DetNet is not.
We have heard the concerns about definitely not having 2 separate standards for this stuff. So,
by the way, we have from Jabber 3+, like yes for the forming.
Okay. So questions: if we start working on this stuff, these drafts, whether it happens in a separate working group or in an existing working group like RAW, are you gonna contribute as in writing or helping editing whatever drafts in this space, problem statements, protocol specs, whatever? Can I please see a show of hands of people in the room that would actually do that? So I see about 1, 2, 3, 4, 5, 6, 7, 8, 9, 9.5, 9.7.
How many from Jabba?
So we're about 10, okay, 12, approximately. And can we please get a show of hands if people are willing to review work coming out of the stuff? So that's a lot larger. I'm guessing about 30 or so. Okay. Deborah, did you have anything else you wanted to cover? Okay. Thank you very much for coming and participating. And blue sheet.
Blue sheets, and there is a raw mailing list. If you want to continue the discussion, absolutely use the list. Thank you very much. Can we have the blue sheets back, whoever's currently got them on their seat next to them? And sign it if you didn't on your way out the door. What do I have to do to turn any of this off? Right. Hey, it's gone.